Okay, welcome everyone to today's session of the Chilean Probability Seminar. Today we have the pleasure to have with us Laetitia Colombani. She's a postdoc at CIMAP in École Polytechnique in France, and she will talk about propagation of chaos in a network of FitzHugh-Nagumo. So, Laetitia, you have the microphone.
Thank you for the invite. Even if it's online, it's always interesting. So yeah, I'm currently a postdoc in CIMAP, so in École Polytechnique in France, and I've done my PhD in Toulouse, in France too, under the supervision of Manon Costa and Patrick Catio, and this work is a part of my PhD studies. It's a joint work with Pierre Le Bris, who was a PhD student and who is now also a postdoc. So it's about the propagation of chaos in a network of FitzHugh-Nagumo. So I will explain you what I mean by FitzHugh-Nagumo. I will describe you the model and what is important for this model. And then I will explain you what I mean by propagation of chaos and what are our results. And eventually I will present you the strategy, so the methods we implemented to prove our results. Just to be sure, is everything okay for the connection? Because I'm just, I hope I'm not lagging or anything.
No, not at all, we hear you very well.
Okay, perfect. So, what is the FitzHugh-Nagumo model? The FitzHugh-Nagumo model is used for neuroscience. So, if we enter into a little of details, what we are interested in is the transmission of messages between neurons. So each neuron has his own potential, electrical potential, and it will receive some messages from other cells via synapses, and it will share some messages to other neurons. And the specificity is that when it shares messages to all of the neurons is connected to. So it's not like a selection, and for one message, it shares for 2 neurons, and for another message, it shares to 5 neurons. It shares to everyone at the same time. So what is really important is the membrane potential or the electrical potential for each of these neurons, the incoming signal for the neuron, and the outgoing signal. So we want to model the membrane potential, and since I'm a probabilist, I add some noise from the presynaptic current. So it's the noise coming from the outside of the neuron. We add also a noise from the conductance dynamic. So it's a noise inside the dynamic. So we can think about it like a chemical noise of the system for the chemical reactions in the cell, or a noise coming from the model because the model isn't exact. And we want to add some transmission of potential between neurons via synapses. So originally, the model of FitzHugh-Nagumo is a deterministic model. It has been studied in the 60s by FitzHugh first and Nagumo a year after. And this model describes X, the electrical potential, and C, which is a recovery variable. So it's not a biological variable. It's just a variable which is here so that X has the good behavior. So the specificity of the equation and of the model is that the dynamic of X is in X minus X cube minus C and minus a constant. The dynamic of C is more usual because it's linear in X and in C. And for the following, I will consider Z to be the couple X and C because I will consider a lot of neurons and it will be easier to consider like one letter for each neurons. Here, alpha, beta, and gamma have some constants and are fixed, and the results are true for every alpha, beta, and gamma. So what does it look like? Here is an example of the evolution of X and C. So what is really interesting for us is the potential X. And here is just a choice of alpha, beta, and gamma, and we can see that we have a cyclic behavior. So depending on the parameters, we will have only one spike, so one big potential and then a return to zero. Or we can have some cyclic behavior. It will depend on the parameters. Then, as I said, we add some noise. So the noise from the outside will be on X and will be given by Bx. It will be a Brownian motion. So the differential equation became a stochastic differential equation. And the noise from the inside of the cell, inside of the model, will be given by Bc and will be added to the equation on C. Here, I consider sigma X and sigma C to be the variance of each noise. And the specificity of our model is that we can choose one of them to be null. We need one noise, so sigma X or sigma C need to be positive. Both of them can be positive, but we can have one of them be equal to zero. And then we want to add some noise, transmission of potential. So we add a lot of neurons, and we will add some interactions, Kx and Kc. So Kx will be the interaction on the equations for X, and Kc on the equation for C. So we will consider n neurons, and for each neurons, the dynamic is the same. So we have the same drift with the cubic term, the same noise, and we will add some interaction. Here, the interaction is called mean field because we consider like the mean of all the interaction. It's a way to control the interaction and to be sure that we don't have an explosion of interaction because we have a lot of neurons. And the number of neurons will grow with time, but will grow. And to be sure that the interaction is bounded, we consider the mean field interaction. Here, the interaction is a function, so two functions, Kx and Kc, and it's applied on the difference of the two states, the state for I and the state for the J neuron. Okay. So Zin will be the state for the eighth neuron, so the couple X and C. So when we add some interactions, what happens on the dynamics? So here I just give some simulation before adding some noise. So we only have two neurons. We don't have any noise. It's only the deterministic behavior. And here we don't have any interaction. So what interests us is the first line of the two potential. And we can see that we only have two. So we just have two neurons with cyclic behavior. And we can see that by adding some interaction, we have a change of the behavior. And here the interaction tends to slow down the the behavior of both neurons. So it's just a choice of the interaction. But here we can see that we have like the behavior is still cyclic, but slower. So why do we choose this model? Because we have a lot of stochastic FitzHugh-Nagumo model in the literature. So Leon and Sanson has worked on FitzHugh-Nagumo model so they study the equations for one neuron to obtain some properties like the mixing time, the estimation of the spike rates, etc. And in their model, they consider the noise to be only on C. So it's my conductance dynamic. Michler, Kininao, and Touboul before have studied this model with noise only on X, so noise only from the outside of the neurons. They study linear interactions on X, and they study the behavior of N neurons, so the existence, the uniqueness of the solutions, the stationarity, etc. Baladron, Fasoli, Faugeras, and Touboul, and then completed by Bossi, Faugeras, and Talley, worked also on FitzHugh-Nagumo neurons with noise only on X. They worked on some propagation of chaos and convergence of the system. So here we can see that depending on the authors, noise can be on C or noise can be on X, but there is not a consensus about it. So when we studied it with Pierre, we chose to consider noise to be possible on C and possible allowed on X. Like we can have noise on both of them. We can choose to have noise only on one of the equations. It's as we want. We generalized a little the model. In our model, the interactions will be Lipschitz to be a little more general than the linear interactions too. So about the propagation of chaos and the results we obtained. So what is the propagation of chaos? First, we need some exchangeable particles. It means that we can just label the particles in another way, and the law is the same. So if my first particle becomes the 10th particle, it's okay. We can call that symmetric law. And then the idea of chaos, described by Kac and Snitman, is that if we have K particles, we focus on K particles in a set of N particles. If N tends to infinity, so the number of particles, the size of the network grows and grows, then the K particles are asymptotically IID. So they are asymptotically independent and with the same law. The idea is that even if they are interacting with each other, the rest of the network is so huge that the importance of the little interaction inside the K particles is too little to be important, and asymptotically it will become independent. The propagation of chaos is that it's the idea of propagation of this property. So at time 0, we have the property of chaos, and at time t, the system stays chaotic. So we keep the property of chaos. In our framework, as I said, we can have noise only on C or only on X or on both of them. And we will focus on Lipschitz interaction. we will consider an initial distribution of the particles following mu0 independently. And what interests us is the law of the k-first particles or k-first neurons in the network of n neurons. So we are interested in mu t k n. It will be the notation. And we will measure the distance between this law and a sort of limit law bar mu t k times. So bar mu t is a specific measure I will describe you in like 2 minutes, something like that. And we will see that the distance between the distribution we are interested in and this distribution of independent neurons tends to 0 when n tends to infinity. So it means that the k particles tends to the behavior of k independent particles. How will we do that? So the idea is that we have here k particle, 4 particles in space, interacting with each other. And the idea is that we will compare them to independent particles. So we have some independent particles following bar mu t, and we will compare them with each other in one by one. How do we define bar mu of t? We will describe a system of 2 equations for one ideal neuron. And to do that, we need to do something with the interaction, because in our original system, we have some interactions on particles, and we can't have interaction on one particle alone. So we need to do something to give the same, not the same information, but some idea about it. To do so, we denote k convoluted to mu the usual convolution between the function k and the measure nu. So integral of k of x minus y nu dy. And then the mean field interaction that we had, 1 over n sum of kx on the difference zi minus zj, can be seen as the function kx convoluted to some measure applied on the state zi. And this measure is the empirical measure of the system. So it's a measure giving the information of where are all the different particles at time t. And we can use it to inspire us to find a way to adapt it for one particle and construct a process for one particle without interaction. So the first system is the same than before. And we obtain a new system for one particle, bar x and bar c, with the same drift. And the interaction is given by kx convoluted with the self-measure of the process. So bar mu is the measure, is the law of the couple x, bar x, bar c. And it's like a self-interaction, sort of. The mean field interaction on C will be given by the same idea. So we obtain a system for one particle, bar x and bar c, with the same drift, with some noise given by some different Brownian motion b bar b, and some not really interaction, but convolution for the interaction. Of course, when we write it, we need to be careful because we are defining a system for one particle, depending on the law of the process, but the law of the process depends on the system of two particles. So we can do it, but we need to be careful about it. And we obtain a nonlinear stochastic differential equation of Mackin-Vlasov type. So Mackin-Vlasov type is when we have the law of the particle in the equation of the drift of the particle. Then, as I said before, we want to compare each original particle with a new particle. So we need to construct n particles following this new system. So we will have bar Z1, bar Z2, etc. Who will follow independently this system. The drift is of the same type. The interaction follows the same ID, and we will have some coupled Brownian noise to have the information we want. About our results, what have we proved? So, as I said, we need Kx and Kc to be Lipschitz, so we will give Lx and Lc. And as I said, we can have some noise to be null. One of them needs to be positive. We obtain a first theorem, which is a non-uniform in time propagation of chaos. So we consider the Wasserstein-1 distance between both measures. So the measures we are interested in and this limit measure. And this distance is lower than k over square root of n times exponential of Ct. So it's a usual result for propagation of chaos. But if we want a large T, we need to have a large N to compensate in the bound. So we wanted to have a better result with a uniformity in time of the propagation of chaos. To do so, we need some conditions on Lx and Lc, the Lipschitz constants. And in this case, we can control the distance to be lower than k over square root of n. And we don't have any dependency in t, and we don't have any exponential of t. It was the main point. What I don't say under some conditions on Lx and Lc is that Lx and Lc needs to be small enough. We have some explicit bounds, so it depends on the parameters, and the explicit bounds are given by some computations. It's not as easy as Lx needs to be lower than 1. We need to do some computations, but we have some explicit conditions. Now, how do we prove these results? So the strategy was a coupling method. In fact, when we want to control the Wasserstein distance, we need to understand the Wasserstein distance. So the Wasserstein distance between two measures is the infimum on all the couplings of this measure of the expectation of the distance between the two particles or system of particles. So usually we choose a good coupling, and it's enough to obtain a major bound of the quantity. Here we will have two choices: the choice of the coupling and the choice of the distance. We can play a little with the distance because we are not we don't need to exactly use the distance we are interested in, so L1 distance. We can choose a major bound of the distance. So we will have two strategies for the first theorem and for the second theorem with the uniformity in time. For the first theorem, we use the synchronous coupling. So it's like the naive idea, because when we consider the Wasserstein distance, we can major bound it by this quantity, so the expectation of the L1 distance of the the major bound, the expectation of the L1 distance of the difference between xi and bar x and c minus bar c. And then we just need to study the dynamics of the difference. And if we choose the noises to be equal, so bar b equal to b and bar for x and for c, then if we study the dynamic of the difference, we just have the drift on x minus the drift on bar x, and the interaction and the pseudo interaction for bar z. So we only have a deterministic behavior, and we can't control the deterministic behavior. So if we consider the L1 distance between z and z bar, we can control this L1 distance by itself and by the interacting part. And the interacting part can be decomposed by the Lipschitz property and the law of large number, and we can control it. So finally, we obtain some good bounds, and with Cornwall's lemma, we can prove the first theorem, so the non-uniform in time propagation of chaos. So this easy idea is enough to obtain some propagation of chaos. But as I said, we wanted to have more than the non-uniform in time propagation of chaos. To do so, we need to change a little the coupling method. So here, we will consider not exactly the L1 distance, but a modified L1 distance. So we have a delta, but it's not really important. And we will have a function f, a good function f, which will major bound the L1 distance and which will help us to obtain the boundary we want. We also need to study the dynamic of the difference, but here we will keep some noise to obtain some better results. In fact, what will happen is that when x is equal to bar x, the deterministic behavior is enough to obtain the uniform in time propagation of chaos. So it's sufficiently quick to obtain the uniform in time propagation of chaos. So we don't need some noise here, and we can consider a synchronous coupling. In the orthogonal subspace, it's not enough. So we need some noise to maximize the variance and to help us to bring the particles together. Then we will have some non-synchronous coupling, because we will mix some reflection coupling and synchronous coupling depending on the space we have. So just to focus on couplings and what I mean by synchronous and reflection coupling. So the synchronous coupling is the one we used before. When B is equal to bar B, it means that if I have a particle Z with some noise B and a particle Z bar with some noise B bar, the noise are the same. And when I'm considering the distance between the two particles, the Brownian noise is cancelled when I look the dynamics. So the contraction can only come from the deterministic drift. So if the deterministic drift is good enough, it's okay. If not, we need to choose another method. The reflection coupling is when we choose bar B to be equal to minus B. So we have a particle Z with a noise B and the particle bar Z with the noise bar B, and the two noises will be opposite. Here it's a good picture because here both of the noise will bring back together the particles. In some cases, in some cases, Z bar will be far away than X, but we can control that. So this method maximizes the variance of the noise in the desired direction. So here I want X to be close to bar X, but we need to modify the distance by a compact function on a compact set. The idea is that the concave function will allows the control of the distance between both particles, but we need a compact set to do that. So how do we do that in practice? We will have two Brownian noises. A Brownian noise synchronous, SC, and with reflection, RC. We will have two functions, so phi synchronous and phi reflection, and we have some properties to be sure that we obtain a good Brownian motion after. Then we can define both Brownian motions, and what is really important is the last line, is that the difference between B and bar B will be given by the function reflection, which gives us the information that we are in a space where we need some reflection, and the Brownian motion of the reflection. Then we can distinguish three regions with the two functions phi of synchronous and phi of reflection. So when the particles are near the space where X is equal to bar X, we consider the synchronous coupling because it's enough, it's sufficient. When the particles are not in the space but are in a compact set, we can consider the symmetric coupling with my concave function. And if a particle escapes to infinity, so we are not in a compact set anymore, but we can use a Lyapunov function to bring the particle back. For the Lyapunov functions, so just a little point, we used two Lyapunov functions. So the first one was a usual quadratic function, which is used a lot for Lyapunov functions, and it was sufficient to have bounds on the moment of the particles. But it was not sufficient to obtain the boundaries we needed. We needed a better control of the noise, so we had another Lyapunov function, which is given by tilde h and some formula, big formula. And what is important with this Lyapunov function is that then we will be able to define the new distance. So the distance between both system of particles. So here that ZJ will be the first original system of particles, and Z prime J will be the limit one. And the sort of new distance will be given by the mean of the function f, the concave function f of the L1 distance between both. And we will multiply it by 1 plus the Lyapunov function for the first particle and the Lyapunov function for the second particle, and some interacting term with Lyapunov function at the end. So all the informations will be in the new distance. Then, with this coupling and this distance, we can work on the dynamic of the system with a good choice of parameters, so a good choice of the function f, a good choice of the speed c, etc. We will be able to prove the contraction in various spaces, so the three regions I've talked before. And with the Grunwald's lemma, we obtain the second theorem with the uniformity in time for the propagation of chaos. So this idea of mixed coupling has been already studied before. So Lindvall and Rogers has worked on the coupling of multidimensional diffusions by reflections. So it was only the reflection coupling, but with multidimensional diffusions. And later, Eberle and Zimmer has worked on sticky couplings for diffusions. So we are not exactly in the same context. It's not exactly the same type of couplings, but they proved the contraction of processes on a linear subspace, and they worked with different subspaces, with different couplings to prove the results they wanted. Then Eberle, Guillain, and Zimmer worked on some mixed coupling for Langevin equations. And my co-author Le Bris with Guillain and Montmarché worked also on these couplings in some context in which FitzHugh-Nagumo were not because of the cubic term. So to conclude, we obtained so the propagation of chaos for FitzHugh-Nagumo processes, but more importantly, the uniform in time propagation of chaos when the interaction is small enough. There are a lot of perspectives. We can think about other types of interactions, because here, as I said, we were in the Lipschitz interaction, in Lipschitz context. But if we want to focus on neurons, we can think of some indicator with some threshold to say that we have interaction only if two particles have very different potentials. But we would lose this idea of Lipschitz interaction. And we can also focus on some interaction where we don't need to have the information of both states of neurons. Like we only need to know what is the state of the other neurons who is giving information, but the neurons, the eye neurons, the state of the eye neurons isn't really important. I would also like to add some environmental noise. So the idea of the environmental noise is that we have some equation with a drift, but we don't have individual noise. We have a noise which is the same for all the particles. So here in neuroscience context, it means that, for example, we are focusing on a part of the brain, but we can have some noise coming from another part of the brain or coming from the outside of the individual, of the human or animal, etc. And I would like to understand what would be the behavior of FitzHugh-Nagumo processes in this context. We can also consider individual parameters, because here I've considered, so we made two assumptions. We made the assumption that the network is homogeneous. So all the neurons are copies of each other. They have all the same parameters. And we made the second assumption that all the neurons are connected with all the neurons. We don't have any subgroups or anything, and everyone is communicating with everyone with the mean field interaction. So we could improve this work with these directions. I would also work on synchronization of neurons. So Poquet and Luçon has already worked on some synchronization of neurons in some context, because in fact, biologically, we know that neurons can have a cyclic behavior, but a synchronization between them. For example, to control the cardiac rhythm or the respiratory system and other parts also. So it's some important questions about FitzHugh-Nagumo and neurons. Thank you for your listening. Thank you for the invite. All this work comes from the article "Propagation of Chaos in Mean-Field Networks" of FitzHugh-Nagumo published this year in Mathematical Neuroscience and Applications. And feel free to ask any question you have.
Well, thank you very much, Laetitia, for the talk. I think we can thanks Laetitia for the talk first, and then we pass to the questions. Oh, okay. Is there any question?
Yo.
Go ahead, Joaquin.
Okay, thank you. Thank you very much, Laetitia, for the nice talk. I have one question. I should know the answer because I read a paper by some of the papers by Andreas Eberle, but I forgot. Or I didn't really understand. What was the rationale behind the Lyapunov functional and the way it is modified, or in order to construct the metric, the distance, in this case, the H, where does the H come from, and why is the H tilde chosen like that in this setting?
I think Laetitia is mute. Unmute. You are mute again.
So you are mute and then.
Laetitia, you are mute again.
But what happens?
No, you're right.
Okay, I don't understand what happened, but okay. Okay, so your question is about the choice of tilde H. Is that right?
Now Joaquin is muted. Joaquin, desmuteate.
Sí, aquí estoy. I'm here.
What was your question? What was about H tilde?
Yeah,
so
my question is
the choice of.
Yeah, where does the Lyapunov functional come from, and and how is this how it is the H tilde built? I mean, because the H tilde is the one that appears in this modified distance. So what is the relation, or how is this relation between the two? What's the intuition, or what's the reason to consider this H tilde in the definition of rho?
Okay. So to be honest, Pierre chose this tilde H because in examples he worked with this was a good function, and I don't really know why how we can think of this kind of function with exponential of square root of h. So I don't really know, because when I asked, it was more like some people tried with this function and it works, so we chose these functions. I'm not sure it's really. I'm not sure.
And the first, the H, at least it is related to. I mean, what was the H? Yeah, it's related to some part of the dynamics. Okay, there is the X.
Yes, it's like it's a quadratic function, and it's linked to the yes to the dynamic of X and C.
So, yeah, so that one seems to be okay, to be well connected to the dynamics, and the other one probably there is some indication of Ito function, Ito formula, which
yeah, and we can yes, tilde H is also good because we can so the idea at the end is to compare rho to the L1 distance, and with tilde H we have some good major bounds and lower bounds, and it allows us to do so.
Okay, thank you. And maybe just one small comment regarding synchronization. Maybe you can take a look at the paper that we have with Hector and Mireille Bossy, which is maybe complementary to the paper by Luison Pouquet. But maybe, I mean, probably the approaches are different, but yeah, in case you would like to look at alternative points of view.
Yes, thank you.
Okay, thank you very much for the nice talk and for your answers. Okay.
Thank you.
Is there more questions?
I have a question, or several. Thank you very much for your nice talk. I liked it very much. Well, I have several questions, actually. The first one about the Wasserstein distance. Is it normalized by the dimension, by k, or not?
Here, no. We just no.
Okay. So when you get, for instance, in the uniform or in any of the results, you get a k on the upper bound, right?
Yes, exactly.
Okay. So my question then becomes, if you divide it by k, which is typically done when you want to avoid the dependence on the dimension or the number of particles, that means that pretty much on the right-hand side, you get something that does not depend on k.
We should, yes.
Okay, so now the question becomes, I saw that your estimates do your estimates work when you consider the full distribution instead of just k particles?
Oh, no, I don't think so. No, I don't think so, because we sort of need the other neurons. Yeah, I'm sorry. I'm sorry. I don't know how to what to say more, but I don't think.
but can you please show the next slide or the one after that where you bound no, the next one you write an upper bound for the Wasserstein distance in terms of the expectation of a sum divided by n. Yeah, that one.
Yeah.
So at first glance, it would seem to me that if you took the full set of marginals, then you still get this inequality.
Yes.
Or not. So maybe your result can be extended to that case, or maybe not. I mean, maybe there's something later in the proof that needs to have only k marginals. It's a question.
Yes, I don't remember exactly, but I think yes. So there is a step where we need to consider only k neurons.
Okay.
But I need to check more precisely to be sure.
Okay. I have more questions, but maybe someone else wants to ask.
I had a really naive question, I think. I don't know if you can hear me.
A little, yes.
Yeah, so we are to... Now it's better? Or the sound is not too good? Maybe. I don't know how to raise. I can raise my voice.
That's okay, like that, it's okay.
Okay, so what happens if one particle of yours does not interact with all of the system? But let's say that you start with an Eberle graph of which things will be able to interact with each other. Could you also prove like propagation of chaos if the parameter p is not small enough? Let's say like in the connected case of an Eberle graph. And then, I mean,
okay.
if you interact with your neighbors in that graph.
Yes, so it's not the same tools in this kind of work when we don't have a complete graph. So I'm not sure if we could use some couplings methods in this case. I need to look at it because I know that there are other methods for proving the propagation of chaos. And I'm not sure a coupling method would be the good one if we don't have a full connected graph.
Thank you.
Is there any other question in the audience? No? Because I have, I think, simple to formulate, but maybe not so simple to answer. But what happens if you consider the diffusion term not constant? Is it possible to do more or less the same?
So so the sigma?
Yes, sigma instead of a constant, a sigma of x or of z.
So I think we can do some things, but the difficulty is that we will need to take it into account in the coupling, because here it will depend on the x, and we would have another one depending on the bar x. And but maybe something is possible with good function of x, of course, because since we are considering, where is it? Since we are considering the function phi of the difference between both states, yeah, we would need to be really careful to understand how to add the sigma of x and the sigma of bar x. But maybe something can be done, yes. I'm not sure. It could be a direction.
Okay. Thank you very much for the talk. It was very, very nice.
Thank you.
So, well, we thanks again to Laetitia.
Thanks for the invitation.
I think Roberto had another question.
No, if you want, Roberto, you can go ahead. I think we have still 5 minutes.
Yeah.
Okay. One final question then. When you have the conditions for the uniform in time propagation of chaos, do we know anything about convergence in time, like stabilization or something?
Yeah, no. We need to work on that.
Okay. Because in this setting, usually when you have propagation of chaos uniform in time, it's partly because you have some good behavior for large time too. So
yes, we expect that, but we have not took the time to do that.
Okay. Thank you.
Thank you.
Well, so we finished in this way the first part of the seminar of today. I will stop the recording so we can wait for the next talk.